Hello. So in the previous video, we saw different preparatory methods of alkenes. So today, let us see properties of alkenes. The first one is physical properties. Okay, so physical properties of alkenes are the same as alkenes. Like we have the basic points, we have boiling point, we have melting point, and some other extra points. So let us see. So boiling point of alkenes is directly proportional to their molecular weight. So when there is more molecular weight, then the boiling point will be more. So branching, when there is more branching, the boiling point will be less. Okay. So cis alkene has greater boiling point than trans alkene because polarity. So in case of cis alkene, like here, like this is cis alkene, right? So here there is polarity. So because of polarity, the boiling point will be higher than that of trans. Now, melting point is directly proportional to molecular weight as usual, and it is not related to branching. And transalkene has greater melting point because packing. So the atoms are easily packable like this. Okay. So the reason is packing. And here from 5 carbons to 17 carbons, alkenes are liquids, and greater than 17 carbon, the alkenes are solids. Till 5, they exist in both liquid state and gaseous state, mostly gaseous state. So these are soluble in organic solvents like benzene, toluene, and so on. Those are physical properties of alkenes. So chemical properties of alkenes, let us start. So what are chemical properties of alkenes? They undergo electrophilic addition reactions, means electrophile gets added. Okay. And then free radical addition reactions. Free radicals mechanisms take place. Okay. So electrophilic addition, let's see the basic mechanism. Simply, the double bond is broken and then the electrophile is attached first. That is why it's electrophilic addition. And then the nucleophile gets attached. Okay, so this is electrophilic addition reaction mechanism. So it occurs in two steps. Okay, so the first one is the rate determining step, formation of intermediate or formation of carbocation. So first, what happens is this solvent, whatever we are using, the electrophile and nucleophile breaks. Okay, and then first the electrophile, what happens? This double bond is taken by one carbon, forming a negative charge, and then immediately this electrophile, which is positively charged, which wants electrons. Here, electrons are freely available, so the electron goes and attacks there. Okay, at the negative charge. So once the electrophile goes and attacks there, a plus charge is formed, right? Because the electrons are taken from this carbon, so plus charge is formed. So this is a intermediate formation. This is the intermediate. Carbocation is the intermediate here. Okay, and then B minus is there, and then later this is the rate determining step, and then nucleophile, as the electrophile approaches, the bond is broken. Okay, so that is important. And then the second step is attack of nucleophile, and then the nucleophile gets added, and the rate is directly proportional to the concentration of alkene you are using and the concentration of electrophile in electrophilic addition reactions. So this is addition E2 reaction or bimolecular electrophilic addition reaction. So the stability of the product is completely dependent on the intermediate. So as we know from intermediate, inductive effect and stuff, we can find the stability of carbocation. Now, the first very important property of alkenes is addition of HX or hydrohalogenation. So in today's video, let's see only this reaction because it's very important, and we have similar reactions further. So what is addition of HX? Addition of uh, this HX, where hex is halogen. Now, what happens? There is alkene here, HX is added, and addition takes place, and at one carbon H is formed, and one carbon X is added. Okay, so how does this mechanism take place? So, first of all, alkene is there. You take some HX, HCl, HF, or anything. What would happen? We have seen in electrophilic addition mechanism. First, the hydrogen goes and attaches, or first the electrophile goes and attacks. So here hydrogen goes and attacks. Okay, so the hydrogen goes and attacks such that a carbocation is formed. Now, and then after the carbocation is formed, the Cl goes and attacks. Okay, So this is the step 1 and this is the step 2. That is a simple mechanism. Now, here, let's take this alkene. Let's see an example of halohydrogenation. Now, uh, we took this alkene here, okay, and then we added HX. When we added HX, what happened? So, there is a possibility that the hydrogen goes and attacks here, or the hydrogen goes and attacks here. How do you decide between these two? Where the hydrogen goes and attacks. So both can be formed. So here the hydrogen, so here you can see as a plus charge is formed here, first the hydrogen went and attacked here. That is one part of product, and hydrogen went and attacked here. That is the another part of the product. So when the hydrogen went and attacked here, what is a carbocation formed here? Like this. A carbocation is formed here. And then when the hydrogen attacked the other carbon, the carbocation is formed at the middle carbon. Now, out of these two carbocations, which is more stable? So, 2-degree carbocation is more stable, right, from inductive effect. So, 2-degree carbocation is more stable. So, that product which is giving a stable intermediate will give you the major product. Most of the reactant wants to convert into a stable intermediate and thus a stable product, right? So, that is why 2-degree carbocation is more stable. From this, we can come to a conclusion that the hydrogen which is going and attacking here, so the hydrogen should go and attack where it is more substituted. Means hydrogen goes and attacks where there are more number of hydrogens. Okay. So when hydrogen goes and attacks the region where there are more number of hydrogens, that product is the major product. So here you can see 2-degree carbocation is formed where the hydrogen went and attacked the region where there are more hydrogens. Here you have two hydrogens, right? So the hydrogen went and attacked the two hydrogens instead of one hydrogen. Hydrogen goes, attacks where there is more hydrogen. Okay, so that is called Markonikoff rule. We gave it a posh name, Markonikoff rule. That is, it's also called as Markonikoff's rule or Markonikoff's rule. Okay, so when HX is added into an unsymmetrical alkene, we are discussing different cases when it is unsymmetrical only, right? Then H plus attaches to that carbon of double bond that has more hydrogens. This is Markonikoff's rule. Because major product and minor product are forming, halohydrogenation follows regioselectivity, like we saw in bromination, right? Okay. So here, now don't see this. Don't see this. No. This is the alkene you're having. Okay. So this is the alkene you're having. You are adding Hi to it. Now the hydrogen should go and attack where there is more hydrogens. Like here there are more hydrogens, right? The hydrogen goes and attacks here. So CH3, first the double bond breaks. CH3 is formed and then a positive charge is formed. 2-degree carbocation is more stable. Okay. So that is how this mechanism works. So this product thus formed like this. And then the iodine comes and attacks here like this. This will be the major product. And what would be the other case? The other case would be the hydrogen attacks here like this. The hydrogen comes and attacks here. Iodine attacks here. So these are the two products. Okay. So these are the two products. So what will be major, what will be minor? You can decide using carbocation stability. And then anyhow we created Markonikoff's rule. Okay. So where more hydrogens are there, the hydrogen goes and attacks here. Now you can see if the carbocation is this, then this will be the product. If the carbocation is this, then this will be the product. What will be major? What will be minor? Markonikoff's rule or stability of carbocation. This is more stable, so this will be major. This is less stable. This will be the minor. Very simple. Okay. So here two hydrogens are there. Hydrogen attacked where there are two hydrogens. Hydrogen attacked where there is one hydrogen. So where there are more number of hydrogens, that will be the major product. So two hydrogens will be given more priority. Right? You get the point. A new case. So there is some contradictory factors here, like this. Now we have a CF3 here. Fluorine is a minus I group, means it withdraws electrons. When it is a withdrawing group, when it is taking electrons, then the stability of carbocation is less. The positive charge on the carbocation is increasing. So when the positive charge on the carbocation is increasing and you have a minus I group or a withdrawing group, then the charge is increasing. When charge increases, the stability of course decreases. So here, when you have a minus I group here, what is happening here? Now, there are two cases. Just look here. Okay. In this case, there are two cases. First, it breaks. Okay. So a positive charge can be formed here, or a positive charge can be formed here, like this. While the hydrogen went and attacked here. These are the two cases. Okay. Now, among these two, what is the more stable carbocation? More stable carbocation will be this, right? Because if the carbocation is here, because of minus I groups, this is going to take electrons. So when it is going to take electrons, this positive charge is increasing. The deficiency on carbon is increasing. So when the deficiency on carbon is increasing, the charge will increase. When the charge increases, the stability of course decreases. So this will be major product. Means it is contradicting, right? So here the hydrogen went and attacked where there are less carbons. Means let's come back. Okay. So the hydrogen went and attacked where there are less number of carbons because presence of a minus I group. So this will be a major product because we saw because of inductive effect. Because of destabilization of carbocation. Here the carbocation is less stable according to Markonikoff rule. So that is why we got a new rule called anti-Markonikoff effect. So here you can directly see because of minus I groups, you can tell that anti-Markonikoff addition takes place because it is anti. Now, anti-Markonikoff effect or peroxide effect or Karash effect, what does it mean? When HBr, only HBr, okay? This is possible only when there is HBr. Here we are discussing because minus I group is there. The anti-Markonikoff effect is different from anti-Markonikoff addition. So what is anti-Markonikoff? When there is HBr, only HBr is added to unsymmetrical alkane as usual, hydrogen attaches to the carbon of double bond which has less number of hydrogens. And this reaction takes place when in presence of peroxide. So whenever there is peroxide, the things become reverse. So when there is no peroxide, Markonikoff addition takes place. But when there is peroxide, anti-Markonikoff addition takes place. And this peroxide effect takes place only in case of HBr. Okay, simple. Now, as we saw the rule, that is anti-Markonikoff rule, what would happen? First, what are the two cases? The two cases are, first, you have CH3, CH, positive charge, hydrogen went and attacked here. Hydrogen went and attacked here. This will be a positive charge. And the other case would be like this. Wait. CH2 and then CH2 plus. These are the two cases. So the hydrogen, where there are less number of hydrogens, the nucleophile attacks. So here, okay, hydrogen, sorry, the hydrogen goes where there is less number of hydrogens. So here it went to the more number of hydrogens. So it will be minor product. And here it went to less number of hydrogens. That's why it will be major product. This is called peroxide effect, and this happens only when there is peroxide. So we saw here major product will be this one. The Br attaches to the positive charge. Anti-Markonikoff addition does not occur with HF, HCl, HI. It only occurs with HBr and peroxide. Okay, this is called peroxide effect or anti-Markonikoff effect. So mechanism of anti-Markonikoff, why this is happening? Now let us see. Now we took the example here. So whenever there are peroxide and all this stuff, what would happen? Radicals are formed. So here, what would happen? A homolytic cleavage takes place and radical is formed. Once radical is formed, the Br radicals are releasing because of the H nu. So Br radicals are here. Okay. So this Br, it attaches here. Or this Br can go and attach here. Right. So this attachment is more stable. Okay, that is why, as this is more stable, the bond is formed like this, not like this. Okay, so that is mechanism of anti-Markonikoff addition. Okay, let me clear. clear. No, that's it for today. So we have seen Markonikoff effect and anti-Markonikoff effect, and in the next video, let us continue with the halohydrogenation, and let's see the more stable, like 100% Markonikoff product and 100% anti-Markonikoff product. Okay, thank you. Have a nice day.